So I'm Kyoungdeock Park. I also go by Daniel, so if that's easier for you, you can just call me Daniel. I work at the Department of Applied Statistics, Statistics and Data Science, and I'm also affiliated with Institute of Quantum Information Technology at Yonsei University. So I'm going to talk about quantum machine learning for precision medicine, the opportunities and challenges that quantum machine learning presents. But probably just by looking at my affiliation, you might wonder what this guy knows about precision medicine. And you are absolutely correct. I come from no background in bio, life science, medical physics. But I have been working on quantum computing, quantum machine learning for some time. So I'll try to provide some perspective on this coming from quantum computing scientist. Right, so this is a layperson's picture on what precision medicine is about. Previous speakers already gave very nice descriptions about precision medicine. So my shoulder is a lot lighter. And I hope my picture is not terribly wrong. But I think by listening to previous speakers, I think this idea is more or less correct. Right, so I don't think I need to go through all of this in detail, but the conventional, in the conventional healthcare, we usually have this one-fits-all model, right? We spend lots of time developing a drug, and then we hope that it works on everyone. But in precision medicine, we really want to personalize healthcare, personalize medical services, medical treatment, and so on. And for this, now we have access, the size of the data and complexity of data, they continue to grow. So we have access to this large set of not only medical or bio data, but we also have data about the lifestyle of patient, environment, the diet, whatsoever. So there are a whole bunch of different types of data set that's sitting there to be analyzed, to customize the medical treatment, optimized for each individual patient. All right, so now this makes us to think that this precision medicine is asking for advanced tools for complex and large data analysis. And there is a quantum computer just sitting next door. So, we wonder, what about quantum computer? Does it help us at all? So, that's something to think about. But then now, all right, so what is quantum machine learning? So we are trying to do some data analysis, machine learning through quantum computing techniques. Just to mention very quickly, quantum machine learning is simply doing machine learning on a quantum computer. So we're trying to let quantum systems to learn from data and apply the knowledge that has been acquired from data to some new situations and new scenarios. That's what machine learning is about. And then the only change here is that we're changing the system from classical system to quantum systems. And now, because we changed our device, our machine, from classical to quantum, we are now exploring fundamental limits, the laws of quantum physics imposed on machine learning. So this is quite interesting from fundamental perspective as well. And now we have the ability to, we have access to quantum information processing abilities. So this of course presents some opportunities, but we also have to be careful because now we're basically changing the rules, right? We change the rules of how we compute and how we calculate things. So there are also challenges that we need to think about. When we think about quantum advantages, provable quantum advantages, there are some key subroutines, and I would like to mention quantum phase estimation. And very quickly, quantum phase estimation is basically about finding eigenvalues and eigenstates. It's like a solving linear algebra problem. And sounds like a simple problem, but turns out that we could achieve exponential speed up in solving, in tackling these eigenvalue problems, eigendecomposition problems. And this has so many applications, like solving linear systems. And the famous factoring algorithm also uses this quantum phase estimation algorithm as a subroutine. We can use this to simulate quantum systems. We can perform like principal component analysis. And if you combine it with another famous Grover search algorithm, you can also do like, you can achieve like quadratic speedups in Monte Carlo sampling and so on. So we have so many applications. And now if we look at the quantum phase estimation in more detail, there's a quantum Fourier transform. So this is like another like linear algebra problem. And then these are, I would say, like quantum phase estimation and quantum Fourier transform. They are very important subroutines towards achieving quantum advantages. Very quickly, like in order to implement quantum phase estimation or quantum Fourier transform on, let's say, we have an n-qubit system, then the size of quantum circuits grow basically like polynomially in the number of qubits. And this is actually, if we look at it from purely theoretical perspective, we say this is efficient. However, from experimental perspective, if we really want to build a device doing all of this, this is actually extremely challenging. So the questions that we can ask at this stage is, can we come up with like QFT or QPE-free algorithms? And with these algorithms, can we show some kind of quantum advantage? And when we talk about quantum advantage, we are used to talk about quantum advantages that we can prove. But perhaps, like, you know, as we try to tackle like practical problems, maybe you know, we can be a little bit loose on the proving things. Maybe if we observe some empirical quantum advantages, maybe that's good enough. We might be happy. So, you know, we can think about all of these things. So in machine learning, in fact, there exists several examples that fits into these pictures. They do not use quantum Fourier transform, quantum phase estimation. Hard to prove quantum advantages, but we can kind of, you know, try by doing experiments. We can try to seek for empirical quantum advantages. And at this point, I'm actually very glad that previous speaker, Professor Kyoungdeock, mentioned that precision medicine is all about classification and clustering. I'm very happy for that because from now on, I'm only going to talk about classification and clustering. All right, so for classification, well, classification, it's an example of supervised learning. Supervised learning is an example of machine learning. And supervised learning basically goes like this. So we have some set of sample data that is sampled from some underlying distribution, like some unknown distribution. So let's say we have like n set of data, n number of data, and then the data comes in a way that we have an input and output, right? So, I mean, I'm talking about quantum machine learning. So as an input, we have some quantum state, and there is some output y, okay? So there is an input and output that's given to us, and the goal is to find the relationship between input and output. So we want to build a prediction function hx, such that hx is a really good prediction for y, given some input rho x, some quantum state. And in like quantum Fourier transform free, QPE free approaches in quantum machine learning, there are two methods to approach this. And also Professor Kyoungdeock already mentioned these things, so I'm very happy for that as well. So we have a variational quantum algorithm. Some people call it quantum neural network. They are conceptually same thing in the context of machine learning. So we can use variational quantum algorithm. And in this case, the prediction function is going to be some expectation value measurement performed on parameterized quantum circuits. So we have some input, quantum input rho x, and then you know, we want to measure some observable m, but then rho has been rho evolves under some parameterized unitary. And then we just measure out the expectation, and that becomes our prediction function. There is also what's called kernel method. In this context, kernel is basically some function that measures similarity between two different inputs. So we can actually in the circuit model, it's not so hard to compute the inner product between two quantum states. So a quantum circuit for that is very well known. You know, so we can perform some quantum we can execute some quantum circuit to compute the inner product between two quantum states. So that is a kernel. And then now we can use this kernel in classical machine learning. So classical machine learning constructs a prediction function as a linear combination of these kernels. And it turns out that this can serve as a prediction function for some arbitrary data. Okay. Right, but in either way, actually they have something in common. In either way, quantum machine learning always builds this linear model. It doesn't matter if whether we use variational quantum circuit or kernel method. The prediction function can always be written in this form. This is just a state preparation followed by parameterized measurement. So quantum machine learning is just all about identifying the optimal measurement for the given task using sample data, no matter whether we use variational algorithm or kernel method. Well, turns out that for binary classification task, identifying optimal measurement, this is a well-known problem in the context of quantum information theory, and in fact, an analytical solution has been known since 1960s. And the analytical solution is, as a side note, it's called Hellstrom measurement. Right, so now let's say we have rho plus and rho minus. So rho plus and rho minus, these represents ensemble of sample data for each class. So we have a density matrix, rho plus, representing +1 class of the training sample. We have rho minus, representing -1 class of the training sample. In this binary scenario, using this theory of quantum state discrimination from 1960s, 1970s, we can easily compute the probability to misclassify a given sample. So the probability to commit error. And the probability of commit error is lower bounded by whatever this quantity. And here, d sub tr, this is what's called trace distance. And this measures the distance between rho plus, rho minus, how different rho plus and rho minus are. Okay, so this is just a distance measure. And by looking at this equation, we can see that having a large distance between rho plus and rho minus is good for minimizing this training error, the error in the training process. And it's not so clear from this equation, but we show in our paper that it turns out having a large distance between rho plus, rho minus is also beneficial for generalization. Actually, generalization is like the ultimate goal of machine learning. Because when we talk about machine learning, we want to build a model that generalizes well to unseen data. So this is like the ultimate goal of machine learning. And then in this paper, we show theoretically that actually having large distance improves generalization in quantum machine learning and also robustness against noise. So that's also very important. However, we also know from quantum information theory that this distance measure is contractive under CPTP map. What does that mean? Basically, a CPTP map, it's basically like anything you can do on a quantum circuit. You can think about it that way. What that means is that once we have rho plus, rho minus that is to be classified, given to our model to be trained, the optimal performance is already determined by how rho plus and rho minus are provided. Okay, and whatever we do after with quantum circuits just cannot improve it. Okay, so quantum machine learning is all about given rho plus, rho minus, finding this optimal measurement, finding the set of theta that gives us the optimal measurement. And then now, if we think about doing quantum machine learning on classical data, we have a bit more flexibility because we can choose how to map classical data to a quantum state. So we have this freedom, we have some flexibility. So there are, this map between x to the map that takes from classical data x to a quantum state rho x. This is what we refer to as quantum data embedding. So we are embedding in classical data as a quantum state. So this quantum data embedding plays a very important role in quantum machine learning because of all of this. So now going back to precision medicine, this quantum data embedding is highly relevant. Why is that? Because when we talk about this complex set of data to be analyzed, we are referring to classical data. So in order to apply quantum techniques in precision medicine, usually, so I'm not sure, like if you have an example where the data to be analyzed in precision medicine is intrinsically quantum, I'm not so sure. But the usual set of data that I can think of, they're classical data. So we need some, so if we want to apply quantum techniques here, then we need some way to come up with a quantum state representation of this data. And according to the previous argument, if we are doing classification for precision medicine, we want to design this quantum data embedding such that the distance, the trace distance, whatever, that is maximized. So we know from theory that this is what we desire. And again, this will improve theoretical bounds, both for training and generalization, and also performance against noise. So this is very beneficial for applying quantum machine learning to classical data. And another things to think about when we design quantum data embedding is that we want to come up with something that is easy to implement on a quantum computer, but something that's hard to simulate classically, because this sounds almost like the prerequisite to even think about potential quantum advantage. I mean, if it gives some circuit that's just easy to simulate classically, probably there's no quantum advantage. So these are some basic prerequisites we need to think about. All right, so with that in mind, this is a work we did some time ago. So we came up with a method to improve quantum data embedding. And actually the idea is to use deep learning. And the reason for using deep learning is we wanted to do something beyond the limitations of CPTP map, meaning what you do with quantum circuits. So we want to do something beyond the limitations of quantum circuits. So we use deep learning. So we need something classical. But then here, the objective function of this deep neural network is very unusual, because the objective function for this deep learning, we are trying to maximize the trace distance between two quantum states. So the objective function has to be computed on a quantum computer. So we also need a quantum computer. So this is a good example of classical quantum hybrid algorithm where we need both classical and quantum. Okay, so all right, so we have some subroutine for optimizing quantum data embedding, and if you go and look at our paper, we have lots of theoretical analysis and some experimental evidence demonstrating that this works really well. So now I want to talk a little bit about some examples in precision medicine. So this is, to be honest, I don't even know how to read it properly. L.I.T. PCBA, please help me. Right, so let me just call it L.I.T. PCBA. If I'm wrong, please correct me during the break. So I look at this data, and this is work I'm doing right now with Cleveland Clinic. So big thanks to my collaborators in Cleveland Clinic. So we are trying to apply our technique to do virtual screening. So this data set, it has 15 different targets, and there are a whole bunch of compounds, and each compound is identified as being active or inactive. Like, does this ligand or compound, usually I think they're like some small compound, does it have like active, does it have like some bioactivity with a given target or not? Okay, so this is a classification problem. And as far as I know, these 15 targets, they are all like relevant to either cancer or metabolic disorders, neurodegenerative diseases, or autoimmune conditions, etc. So they sound like they are, to me at least, they sound like they're quite relevant to drug designing and precision medicine. So we train our quantum machine learning model. And we try to build a classifier. So basically what the classifier does is that given a compound and a target, we predict whether the given compound will have some bioactivity with the given target or not. Okay, so that's a very simple problem, but we try to solve it on a quantum computer. This is just an 8-qubit simulation, so not a real device yet. So this is just an 8-qubit simulation result. Very toy problems. So this is just an example, very preliminary data. So we go through some quantum data embedding optimization process, and then after that we apply variational quantum circuit. Okay, so that's one way. Another way is to benchmark our algorithm, we also just apply classical neural network, but we try to kind of, because we're just doing 8-qubit quantum computing, so we try to downgrade the deep neural network a bit, so they use a similar amount of resources. And well, this is just a simulation, but what's interesting to see here is that when we test them on, so we have tested these methods against 8 different targets. And the quantum approach, given the same amount of training resources, seems to produce favorable results in many different cases. I mean, we don't have good understanding about this. This is just an empirical result. We're not really proving any quantum advantage, anything like that. But still, like, encouraging results, encouraging us to for further studies. And again, I would like to thank collaborators at Cleveland Clinic, especially Jung-gu Choi. He's been working quite closely with my group. Second example is to predict protein ligand dissociation level. So this dissociation level rate determines how quickly a drug unbinds from a protein target. So if we have a protein ligand complex, like how quickly do they dissociate, right? And this has an effect on drug efficacy, dosage requirements, and side effects. So analyzing the dissociation levels helps matching the right drug to the right patient. So to me, it sounds like this is also something relevant to precision medicine. So again, with the collaborators at Cleveland Clinic, so we looked at this PDB bind data set. And the task in this example is we want to do the classification. We want to make a binary prediction of the dissociation level. So given a protein ligand complex, is the dissociation level above the median or below the median? So we just want to do the binary prediction. And in this time, actually the number of data is not very large. So we could just use support vector machine. So in this example, we compute the quantum kernel, and then we run support vector machine. And we can also, as a comparison, we can also do a support vector machine with the classical kernels. And then for the quantum model, there are different ways to it provides us some flexibility to design kernels. So we have tested 3 different models. And again, this is an 8-qubit simulation. And at least from this empirical data, quantum is producing very competitive results. I mean, we haven't looked at it very carefully yet, but it's giving us some encouraging results. Right, so I have a few minutes left. I can also talk a little bit about clustering. So clustering problem is very different from classification because we now don't have the labeled data set. We're just given a whole bunch of data points, and then we just have to find patterns within them. And what's interesting here is that we can actually transform this clustering problem as a problem of finding the ground state of Hamiltonian. Okay, so we can map this clustering problem. We can map the objective of the clustering into the Hamiltonian. And then we can also encode some constraints in clustering. Maybe there are some limitations in the size of the cluster. Maybe we want the density to be this and that. So we can impose some constraints on the Hamiltonian as well. And then once we have clustering problem is the problem of finding the ground state of Hamiltonian. We can solve it through quantum phase estimation, variation quantum algorithm, QAOA, quantum annealing, whatever. And now because we have access also to quantum annealer, why not just try it? So we tried it, and well, this is not exactly like a medical or a bio data. This is not relevant to precision medicine, to be precise. But we just tried this on some toy problem. Clustering of 170 data points, about 170 to 200 data points, and then we just compare it to like vanilla k-means algorithm, the typical algorithm that you would use classically, and very encouraging to see that actually most of the results were very competitive against k-means, or actually some of the cases actually we got better results than the classical algorithm, on a real device. So I think that was quite interesting. Finally, another example of unsupervised learning is anomaly detection. No label data. We just know that given the given data set is normal. So we train our model, and then given a new set of data, given a new data point, we want to determine whether the given new data is a normal data or anomalous data. I would think that this is also highly relevant in precision medicine. So there is like a classical deep learning based way of doing it, and then we basically did something very similar, but we basically built like a quantum model for doing this. And then again, these are not exactly medical data or bio data, but we try to detect some anomalies in image data and also like credit card fraud detection. And I don't have a very good visualization here, but the idea is that here we did 8-qubit simulation again, but in this time we also have incorporated the noise model of IBM-Q device, and we see also very encouraging result that this new approach, quantum QSVDD, this is our method that we developed here, seem to produce very good anomaly detection results. Even actually better than the classical method. All right, in summary, quantum data embedding, this is essential for applying quantum machine learning to precision medicine. It significantly impacts training, generalization, and robustness against noise. And in our lab, we came up with classical quantum hybrid algorithm that optimizes all of these aspects. And then with collaboration with Cleveland Clinic, we have some preliminary results on the LIT PCBA dataset and also PDB bind dataset showing some promising performance. So I have one final slide telling you about challenges and opportunities of quantum machine learning, but I think my time is up, so I'll just put it up here and I'll end here. Thank you very much.